Thank you very much. First time here, I'm happy to see that my work is relevant to this workshop. So this is about intelligent information acquisition, which is very important in very complex environments. And also representation for decision support. And I was very happy to see efforts for visualization, which is very important for humans to understand that complex environment. So everybody here recognizes the importance of humans. Of course, technology is a natural extension of our capabilities and an augmentation of our capabilities, and it shouldn't be seen as a replacement. So how does technology help us in order to augment our capabilities and understand what is happening in our environment? So many slides, I will leave some slides for reference and share them with the audience later. So what I'm concerned about is all these challenges, new challenges that we're facing as a humanity, which are also opportunities. And we have all these amazing methods that we have created. And challenges keep evolving, they're becoming very different. And we have modern day challenges in irregular migration, for example, attacks on civilians, cyber attacks, that is something very new for humanity. So how do we deal with all these? So we have to operate in very complex environments. And the maritime domain is very complex, but it's not just the maritime environment, it's all the environments that we have, indoor environments, urban environments, the human body is very complex. CyberPhysical systems that we have built are very complex and susceptible to attacks. So challenges everywhere, including the maritime domain, that is the focus of this workshop. And our response will come with also new technology. So humans without technology cannot, of course, deal with all these new challenges. So augmenting our capabilities with methods, hardware, cyber-physical systems, and also methods for signal processing and machine learning, which is more of the focus of this talk, will help us make sense of the environment. So we have evolving challenges, therefore we have to have an agile response, not a static response, static sensors that just sense in a certain way the environment. We have to have intelligent data collection. So what I'm considering focuses on solving part of the problem, so the signal processing aspect. And then we need control methods in order to implement all these things that I'm going to talk about. So we have a lot of other capabilities that are needed. So I will focus here on these cognitive systems that are able to have reconfigurable capabilities, change the way they sense the environment, change the way of processing the data, change the way of communicating between them or choosing when to communicate and so on, and also actuation, moving in order to be able to adapt to the environment. And we saw yesterday efforts for creating morphism, changing in structure of this cyber-physical system. So we have also heterogeneous data collection and heterogeneous capabilities. So all these different vehicles, autonomous aerial, surface, underwater vehicles, have different capabilities, and they all need to work together somehow. So how do we integrate these capabilities and are able to execute a mission based on all these different capabilities and constraints that we have? So these are the problems that I'm concerned with, and they can solve general problems, situational awareness, also including the maritime environment. So the idea here is that each entity, each cyber-physical system, or each human with the individual expertise know something about the environment. So we have partial information. All of us have partial information about what is happening. So it's very important to be able to have methods for data fusion, taking that heterogeneous data and fusing them together in order to create a common operational picture from which we can take strategic decisions. And from those strategic decisions to be able to provide configuration commands to these autonomous systems in order for them to execute the tactical, to handle the tactical method of executing those missions and bringing back again that partial information for fusion and so on. So one way to do that is to consider the Bayesian method. So I will go to some level of detail because some of you already know these things. So the idea here is that we have a model of how the environment, for example, is changing, a dynamic environment is changing, or, for example, a vehicle is moving. So we're trying to track the motion of a vehicle. We want to know the position, velocity, acceleration, and so on. So we have a model of how this dynamical system is moving. So from that dynamical model, we can provide a prediction in the future of what's going to happen, how that target is going to appear, the state is going to be in the future. And we take that prediction and we take new data and we fuse that prediction with the data in order to update our estimate of how the target behaves, the moving vehicle behaves. And that can be also used in estimation of the state of the environment in the maritime domain, for example. So just an overview here. So we predict having that prior information here with a model using past measurements, no new measurements yet. We make a prediction into the future, and then we collect new measurements. And with these new measurements and the model, we fuse them together in order to update our state. So there's always an uncertainty. So our state always comes with an uncertainty. We have a probability of what the state will be, of what the position or velocity of a vehicle we are tracking will be, due to the uncertainty of the measurements and also because of modeling errors. So this is the general Bayesian sequential estimation, where we have fusion of prior information with current measurements. The problem is with this formulation is that we have non-linear models, non-Gaussian distributions, so we cannot solve these equations in closed form, analytical form. So we need to use sequential Monte Carlo methods or particle filtering. And also we have these heterogeneous assets that we need to integrate their capabilities, and also we have the problem of heterogeneous data fusion. So that simple formulation cannot work in general. So what we need to have is cognitive sequential estimation, which is based again on Bayesian methods. So the idea here is that we make a prediction of how the state is going to be on the next time step, where the target is going to appear, the moving vehicle is going to appear in the next time step. And then we can solve an optimization problem on how to configure our reconfigurable nodes in order to improve information collection about that vehicle. So for example, if some underwater acoustic sensors are listening to a boat somewhere and kind of having a rough estimate of the direction, the position of that moving ship in the sea, they can instruct the fusion center to command an imager to turn to the direction where the ship is expected to appear. So that's configuring this node to collect improved information on that vehicle on the next time step. Or if we have a radar sensor, we can reconfigure the waveform parameters of that radar in order to transmit the appropriate waveform that is going to improve the illumination of that moving vehicle and improve the information collection from that vehicle. So with the collaboration of various sensing modalities, we can command our nodes in order to improve information collection at the next time step. And this consists of solving this optimization problem to minimize the expected mean square error by finding the appropriate parameters of our moving nodes. For example, an autonomous aerial vehicle should move with a certain path in order to cover an area where the vehicle is expected to appear at the next time step. So different configurations for different vehicles. And after we configure our vehicles, our nodes, then we proceed to the data collection, which is more informative based on the prior information that we have, in order to then provide fusion here at this step. So again, fusing prior information with measurements, but measurements that are biased in order to provide to us better information about what we are trying to estimate. And again, this with nonlinear measurements, we have the problem that this formulation doesn't work. We cannot evaluate these integrals in closed form. So what we can have here is Monte Carlo methods, a Monte Carlo approach. So the idea here is that each of these dots represents, let me see, each of these dots here represents the position and velocity of a ship on the surface of the sea, for example, right? So the state. Now, why do we have many dots? It's because we don't know exactly at present where the ship is. There is some uncertainty because of uncertainty in the measurements that we have collected so far, and also uncertainty in the model that we are using. So each of these possible states is associated with a probability. So we have a discrete probability distribution here, right? So even at present, we have some uncertainty of where our moving vehicle is that we're tracking, right? So what do? We take each of these hypotheses of what is happening right now, and we project them one step into the future. It could be 1 minute, 4 minutes, 1 hour ahead, depending on the dynamic environment and how fast the state is changing. So we are predicting where our target, for example, will be at the next time step. What will be the velocity? What will be the state of the environment one step ahead? What will be the weather during the week? So this is prediction or forecasting. And there are many possibilities. Like we have seen yesterday, there are two possibilities of how the weather is going to be this week, right? Each of them is associated with a probability of what's going to happen. So we have different scenarios here, different hypotheses. So the question is here, which of these hypotheses are more likely to happen and which are less likely to happen? For that, we need new measurements, right? But instead of statically collecting measurements from studying non-configurable sensors, we're going to use the prediction to configure our intelligent sensors in order to be able to provide improved information, okay, based on what our prediction is. So for example, let me take an example here of a foveal node. A foveal node is like our eyes. In the forward direction, we have high resolution, and in the foveal region, the peripheral region, we have less resolution. And this is very good because we can have, if we have an adaptivity, we can have our moving vehicle be in the high resolution area of the node. So can we do that? Can we know where the target is expected to appear? So based on the position and velocity of the target, using the measurement model, we can map onto the measurement space of any sensing node that we have. For example, here is angular measurement. So using this projection from the state space to the measurement space of the sensor, we can identify some resolution cells out of all these resolution cells where the target is going to appear to the sensor with higher probability. So in that sense, we can just select a very small subset of these measurement resolution cells, which we can actually sense, right, with high resolution. So this is adaptive sensing. Also, we are not going to process the entire measurement space. We're going to use adaptive processing and just only process that part, that subset of the measurement space. And that, as you know, for the people who are working with practical systems, is very important. You use a smaller processor, lower power, longer endurance in the maritime domain especially. So this signal processing method is very important for saving energy and also improving higher information. Also, just by processing this small subset of the measurement space of that particular node, that means that we have sufficient statistics that contain all the information that we need to know. Therefore, we don't have to communicate the entire measurement space. We just need to communicate in low bit rate, and we still get the whole information. So again, saving a lot of energy, a lot of power for our autonomous system. So energy here is saving in sensing, improved sensing, processing, and lower power. So what if we have a different sensor than this? What do we have? A radar sensor, an acoustic sensor, and so on. The same exact process happens in parallel. So the fusion center takes this prediction, translates it to the measurement space of each sensing modality, and communicates to that autonomous node what processing operations, what sensing operations, the path plan, and so on, that they need to take in order to provide to the fusion center the information that is actually needed and not process everyone and look everyone in the measurement space. So the idea here is that the maritime domain is very complex and very vast. We cannot have enough sensors, as has been said yesterday, to sense everything, to process everything. So this method is going to enable us to intelligently go and take the information that we really need and not all the information in the maritime environment. And the same thing happens in parallel here for all sensing nodes. We can have any type of sensor, autonomous system here. We use the same process. The data fusion center can communicate the configuration commands. So this handles the capability integration of heterogeneous capabilities. We know for each heterogeneous node what needs to be done, what they need to do to improve the information collection. Now, what about data fusion? The idea here is that when this data come back to the fusion center, each of these hypotheses gets a vote from each node. So that vote is translated to a probability distribution. So eventually, after all these nodes have voted, to say it simply, each of these hypotheses becomes a probability of how the state is going to appear at the next time step. And of course, this becomes the current time step now, and we project once again into the future. So this is data fusion and heterogeneous capability integration. And it's very important, let me just say the same thing, for those who are interested in cybersecurity. If an attacker hacks onto one of these nodes, this is all the information they are getting. They're not getting the entire information that the data fusion has. And also another aspect is that I would like to move at some point to a decentralized approach. So if anyone is interested in that, we can talk. I'm here to get input from you. So I'm gonna leave these slides as reference, just the high-level diagram of what is happening. So the idea, this is called cognitive fusion, and again, this method needs to work with many other methods, control systems and all that, in order to become operational. So this is very low TRL theory that I'm engaged in here. So cognitive fusion is enabling an agile response to evolving challenges, intelligent data collection. So let me move on to applications. I'm going to talk a bit about past projects we had, and also recent projects that have been recently founded. And one of them is a big project that with partner Labast, and we are very happy that we have that support. Labast helped us a lot to get this project, get this funding, and I'm going to talk about it towards the end. So it's all these heterogeneous assets. One thing we have been working on in the past is adaptive target tracking. So changing the parameters of a transmitted waveform from a radar in order to illuminate targets in a certain way, so that we can see, for example, a strong target to be able to see a weak target in the presence of a strong target. So you see here, those who do radar, they know that due to the ambiguity function side lobes, if you have a target with a big cross-sectional area, the side lobes of that target are going to mask a weak target. So with the appropriate waveforms and the selection of these parameters, we can illuminate the smaller target, push away the side lobes, and also as the two targets are moving with respect to each other, we can adaptively change our transmission in a radar waveform in order to get a better information about that target. So as you see here, the waveforms are changing all the time. The ambiguity function is changing to capture that target. Another thing, I'm not going to go into details very quickly, these sparse measurements we get in the maritime domain, we don't get enough data. There are methods for sparse processing, so we can talk about that if you are interested. So from sparse data, we can get a lot of information, and there's certain techniques that can be used for that. Another example is tracking multiple ground targets, and this can be, the same algorithm can apply to the maritime domain also. Here is a fusion of data. Let me see if this works. To go back and back. So tracking multiple targets using a fusion of image and radar data. So this is an example of data fusion that can be used in the maritime domain also, as well as land and air and so on. So I'm not going to let it run all the way. I had a small part in this Horizon funded project, Bridges, and again, applying cognitive methods, adaptive methods. So the idea here is that there was this decision support system, basically for mission planning, where a human operator will put waypoints in order to cover some areas with high uncertainty. So the idea here is to create an autonomous method where you let this software run for a while, creating possible path plans. And the idea here is that the human is in the loop. After the software runs, it provides to the human user a set of possible scenarios, and the human user, based on their expertise, can choose one of the scenarios instead of spending all this time manually putting the waypoints. This is participating also on this project on the target tracking side. So I'm not familiar with the hardware. You can ask people in this company here who are leading this project on a smart cable, a cable that is able to interface between sensing systems from different manufacturers, providing interoperability between different systems. So translating that data formats in an automatic way. So smart cable. I would talk about a project that is under review right now, but we are very hopeful this week we'll hear the results. I'm excited about it, so I'm going to talk a bit about it. And perhaps we can find collaborations also for European level proposals. This is about creating an open sea aquaculture industry in the Eastern Mediterranean. So the idea here is that Cyprus especially is a very small, has a very small land, but a very large maritime area in its economic zone. And there's a lot of capability of growing food through open sea aquaculture, which is very different than coastal aquaculture, as many of you know, because it's more sustainable due to the stronger currents. We can have bigger facilities, bigger production without impact to the environment. And environmental impact is very important here while ensuring food safety. So the idea here is that when we go out to the open sea, these are just some motivational slides, why we need aquaculture and why in Cyprus, which I will skip. The idea here is that when we go out in the open sea, we lose line of sight, so we need more automatization. Also, going there with boats is more expensive. It takes time and it's inconvenient. So we need new automatization methods for feeding fish. For example, when fish are stressed, we need to be able to sense that so that we don't feed them at that time, because then we won't have the food. The food will be wasted. Also, we need new ICT methods for monitoring these facilities, monitoring the structural part to avoid the damages, and also monitoring the environment for sustainability and also for any criminal activity. So it's very important to have the ICT component on those aquaculture facilities out in the open sea. So the idea behind those types of projects is that it's about the integration of capabilities. So we have all these different capabilities. We need legislation, we need ICT, we need expertise of people who understand the maritime domain to put it all together. So for that, we need funding and a common vision. So the idea here is that we propose this project, OS Aqua, to integrate these capabilities and to enable an open sea aquaculture in the Eastern Mediterranean. But also these practices that we will create through this project will benefit also other countries to create their own facilities. And also we will seek help for any countries who have expertise on that. So the components here will be marine modeling, understanding the maritime environment, understanding the interaction with different other competing industries, and then designing open sea aquacultural facilities that suit that environment, that are appropriate for that environment, and also protecting those facilities with ongoing monitoring, making them more efficient, but also with ongoing monitoring, monitoring the environment surrounding these facilities in order to ensure sustainability. So this is what the project is about, and also it will have the financial and legal framework that will ensure its financial sustainability. So this is an exciting project that hopefully will be funded soon. These are the partners. So hopefully we will be able to create that industry and very soon you will be able to come to Cyprus to enjoy fish with the OS Aqua label that has been grown in the most environmentally friendly conditions and most healthy conditions. So this is our vision for this proposal. So let me talk about the project that was actually funded. We have confirmation for that, and it's about to start. It's going to last for 3 years. So what I'm presenting here is the vision of what's going to happen in the next 3 years. And we have Labast as a partner here. It's about a cognitive decision support system for the maritime domain. So the idea here is that we need more situational awareness for the maritime domain. There's many things happening in the maritime domain. For example, we need to understand what is happening in the natural environment so that we can visualize the destruction sometimes that we cause, so that we are more sensitive to what we are doing to the maritime environment. So how do we assess the impact of human activity? Tourism, especially in Cyprus and of course Mediterranean countries, there's a lot of activity going on, different activities. How do we ensure sustainability and cleanliness of these waters? Transportation of shipping also very dense. How do we plan routes, search and rescue operations? For all this, we need some increased understanding, better than what we have now. How do we secure our societies and designate aquacultural zones, for example, for maritime spatial planning? All this is becoming very complicated due to human activity. To design improved energy generation mechanisms, for that we need a lot of data. So data is very important here. How do we collect that data? And also, after we have all that big data, how do we process them? So we have this very huge maritime environment that is very complex. How do we deal with energy scarcity and lack of connectivity? And when we do get the data, how do we enable humans to make informed decisions? And this is why, looking at all these issues that exist, we propose MariSense, a cognitive decision support system that will be essential to entities that need to make sense of the maritime environment. So simply put, the idea here is that we are going to provide a platform that is going to allow people to share and exchange data, and also take that data and create data-driven algorithms, different types of algorithms that interpret what is happening in the maritime domain. So it's going to be a platform that connects different entities in an easy way. So a scientist, for example, an engineer needs to create a deep learning method. They have to contact different people to try to get data. This platform is going to allow that easy access to data for those entities that are willing to share their data. So it can be seen as a research infrastructure. It can be seen as a marketplace of data and algorithms. And it's a place where people can get easily connected to other entities that have the things that they need. So the idea here is that we will create a suite of software for this platform. And of course, we will open this platform when it's functional to other entities to share their software. Also, we will, and data, of course, we will create a maritime laboratory, the first in Cyprus. So we're just beginning, and we definitely need your help on this. That will give us a steady stream of maritime data, and it will provide connectivity, LoRa, Wi-Fi, and so on, in order for entities to take their hardware, for example, and test them in a real environment. And also, it will be connected to the outside environment, so that maybe someone may be interested to try different cyber attacks, cyber security aspects on these underwater nodes, for example. How does that work when you have LoRa or underwater communications and all that? How do you do cyber attacks? So it's going to be a platform that is open for everyone to go and test their systems, hardware and software. We also will have a strategic partnership between the members of the Quadruple Helix, government, academic research institutes, industry and representatives of the industry and public, and an innovation hub. And the idea here is to enable, through this capability integration, the creation of new products and services that will lead to financial, of course, development, but also the development of products that will help in our efforts for securing our societies, protecting the natural environment, and so on. And we are proud to have a very big consortium for this project, having 5 universities, 6 enterprises, 2 representatives of the industry and public, and very importantly, for the first time, the Ministry of Defense has accepted to enter a research proposal, the Ministry of Defense of Cyprus, and it's a strategic decision also from the Ministry of Defense that opens the door for us because the Ministry of Defense has under its command the search and rescue, the civilian search and rescue aspect, so we have access to that, and that is very important for us because we are interested in search and rescue operations, especially in the Mediterranean. That's very important. So eventually, Marisense will has the vision in the future to become an ecosystem of human and cyber-physical systems, so to integrate all these capabilities. And just a few components here, a suite of software. We're going to have cognitive fusion, and I have talked about it before. Swarm intelligence, so this cognitive fusion that I described will break down when you have a lot of nodes. So we have expertise in the consortium of swarm intelligence. So very important, especially when you're trying to localize survivors that are spreading from a certain area. How do you coordinate all these assets? Cognitive optimization, so being able to, for example, solving the problem, the very complex problem of maritime spatial planning in order to maximize the value while considering all the constraints. So this is a complex optimization problem with constraints. So we aspire to provide a software solution for that. Data-driven modeling, semantic interoperability. So having all the hardware and software from different developers and manufacturers, MATLAB, Python, and all that, running on the same platform. We have an expertise. A partner is an expert on that, and also another partner on hardware, as I have mentioned before. And also the visualization aspect. We are very focused on this cognitive decision support. So being able to take that information and provide it in a visual representation in order for human users, experts or non-experts, to be able to make the strategic decisions needed to command these assets that we have in order to provide for us improved information. And also the GIS component with different layers of information so that we are capable of viewing the information and making, again, informed decisions. And of course, we're going to have validation scenarios. For example, for the industry of, so the Maritime Laboratory, we're going to build 2 buoys, an autonomous surface vehicle. These are just beginning, so the first attempts in Cyprus, so we're bringing that expertise in Cyprus. Of course, people here are very, very much more advanced in that. We're going to have an autonomous aerial vehicle, and also we're interested in how to coordinate these assets more than building them, because advanced systems exist already. I have already very briefly talked about the strategic partnership, which you are invited to join. And we're going to have reciprocal access to different capabilities that we have through that partnership. And also the Innovation Hub that aspires to support new startups. And all of them will help the creation of new products and services for different activities related to tourism, emergency response and planning, and maritime spatial planning. So we're going to have some validation scenarios proving some of the capabilities that we'll create within these 3 years. And with that, we will show that we have done something that is valuable to all. So thank you very much. Looking forward to your input.